Okay, so I'm just going to do these questions that I left you on Thursday. So the ordinary level ones first. The half-life of a certain radioactive isotope is 3 years. What fraction of the isotope remains? So if the half-life is 3 years, then what we can say is... We can say after 3 years, half of the sample remains. After another 3 years, so after 6 years, and it's half times a half, so a quarter of the sample remains. Okay, so that's the process, and so on. So, what fraction of the isotope remains undecayed after 3 years? We've actually just answered that. It's half. Oh, what fraction remains undecayed after 6 years? We've answered that too. It's a quarter. And then what fraction after 9 years? So after 9 years, we do a half times a half times a half, because it's 3, 6, 9. So that's an eighth remaining. So that's that one. And number 4, the half-life of a certain radioactive isotope is 10 years. What fraction remains undecayed after 40 years? Okay. So, same thing, set up the little thing. After 10 years, half remains. So then after another 10 years, so after 20 years, we have a quarter remains. Another 10 years brings us to 30, and it's half, 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 so that's an eighth. And then 40 years, which was what they're asking about, is 1/16 remains. So 1/16 of the sample remains, and it then said what fraction has decayed. So if 1/16 remains, then 15/16 has decayed. Yeah? Okay, and then number 5, just keep the ordinary level ones all together here. The half-life of a certain isotope is 20 minutes. How many half-lives in 5 hours? Okay, so we have after 20 minutes, half. I'm just going to do it out like this. Okay, so the next chunk would be 40 minutes, and that would be a quarter. Next chunk would be 60 minutes or an hour. That would be an eighth. So if there's 3 in an hour, then in 5 hours. So in 5 hours, actually I'll do it to the side, sorry. In 5 hours, there would be 15 half-lives. Yeah, 3 in the first hour, 3 in the second hour, 3 in the third hour, 3 in the fourth hour, and 3 in the fifth hour is 15. What fraction remains undecayed after 3 hours? Okay, so we'll keep going with this. So after an hour 20, it's a 16th. An hour 40, it's 1/32. Oh, going to 2 hours, it's 1/64. After 2 hours 20, it's 1/128. After 2 hours 40, it's 1/256, and then after 3 hours, it's 1/512 remains undecayed. Okay. What fraction has decayed in 40 minutes? Where's 40 minutes? So 40 minutes is this line here. So after 40 minutes, a quarter remains, which implies that 3/4 has decayed. Okay, what fraction remains undecayed after n half-lives? Ugh. Love it when they bring algebra into it. Okay. So after 1 half-life, it's a half. Let's see, can we see a pattern? Sorry. After 1 half-lives, half remains. After 2 half-lives, a quarter remains. After 3 half-lives, an eighth remains. So is it... Oh, that's hard. I think it's 2 to the power of the half-life. Do one more. It's 1/16. Yeah. So 2 to the power of 1 is 2. That's those. 2 to the power of 2 is 4. That's those. 2 to the power of 3 is 8, which is these ones. 2 to the power of 4 is 16, which is these ones. So if it is after n half-lives, then it's going to be 1/2 to the power of n remaining. That's very hard. I don't think that's ordinary level. That's very difficult. But yeah, it was just about spotting a pattern, which is more maths than physics. But literally every other question we did there was very typical ordinary level for this half-life stuff. Okay, so then the higher level ones. 8. So radioactive isotope is a half-life of 2.4 years. Calculate the decay constant. So this was the formula that was just up here. There. T1/2 equals ln2 over lambda. So T1/2 equals ln2 over lambda. The half-life is 2.4. Oh no, that's years. Now hang on. Can't use years. Okay, so what do I do? Multiply it by 365. If I go down the way. So that's 876 days. And then multiply it by 24. It's 21,024 hours. Then multiply it by 60. And it's 126,140 minutes. And then multiply it by 60 again. 75686 seconds is the half-life. So 75686 equals ln2 over lambda. If we multiply by lambda to cancel and multiply by lambda over here and then divide by 756 and then divide by 756 over here, I get lambda equals so ln2 divided by that long number, and I'm getting 9.16 by 10 to the minus 9. And the decay constant, what was it? I think it's per second, isn't it? Yeah, because half-life is seconds, so it's per second is the unit. All right, that's that one. 9. The decay constant of a radioactive isotope is 5 by 10 to the 3 per second. find its half-life. So same thing, just the other way around. So it's ln2 over lambda. So t a half is ln2 over 5 by 10 to the 3. Oh, well, way easier because you have much less conversions to do. So ln2 divided by 5 by 10 to the 3 is 1.39 by 10 to the minus 4 seconds. Just for context, it's 11.98 days. Not necessary, but just... No, it's not. How could... no, it's not. Sorry. I was doing 10 to the 4, not 10 to the minus 4. It's a really, really, really small amount of time. 10 to the minus 4 of a second. Okay, so an alpha emitter has 2.2 by 10 to the 15 atoms undecayed at a given instant. If the decay constant, lambda, is 8 by 10 to the minus 3, find the activity. So, did we actually look at these in here? So this is your law of radioactive decay. A is lambda n. A is the activity, or do you remember the rate of decay? This is the undecayed nuclei. And then that there is obviously your decay constant. So I think that's what we're going to need to use. A is lambda n. Yeah, I mean, and there's not even a huge amount here. It's just 8 by 10 to the minus 3 multiplied by 2 by 10 to the 15. And that gives us an activity of 2 by 10 to the 15 multiplied by 8 by 10 to the minus 3 is 1.6 by 10 to the 13. And the unit for activity is becquerel. So that seems to be it. Okay, I'm gonna do the next questions, and then I might give you one or two of the other ones further down that might be a little bit more interesting. Okay, so this is all higher level. So I should have told once the ordinary level questions were finished. Ordinary level can just get on with their questions. Okay, so the unified atomic mass unit. This is kind of a little bit controversial. We were talking about this when we were in Athlone last week. Bits of this are prescribed on the course and bits that aren't. So I think I'm going to teach it, but if they ask this, it has to be very heavily supported, because the mole in Avogadro's number, okay, I'm going to explain it first and then I'll tell you what the issue is. Okay, so atomic mass. So since hydrogen is the simplest atom and it contains only one proton in its nucleus, scientists use the mass of hydrogen as the unit of mass and expressed all other masses relative to it. So since oxygen has 8 protons and 8 neutrons, it is approximately 16 times the mass of hydrogen. Carbon is, the atomic structure of carbon is 612, which means it has 6 protons and 6 neutrons. So it is 12 times the mass of hydrogen. So that's its atomic mass. We did look at the mass of protons and neutrons, and they're very, very close. I can't remember which decimal place they disagree on, but it's quite far down. It's 10 to the minus 27 or 28, I think, is different. So there was a slight change made to atomic mass to make it unified atomic mass in the 1960s. And this is where, instead of using hydrogen as kind of the base mark and everything else being a multiple of hydrogen, they used 1/12 the mass of carbon. Okay, so I mean the differences here are minute, but taking the mass of a hydrogen atom and multiplying it by 12, taking the mass of a hydrogen atom and say multiplying it by 16 to get oxygen, it's more accurate to take the mass of a carbon divided by 12 and multiply it by 16 to get oxygen. It just gives you a slightly more accurate value, and that's your unified atomic mass unit, which is U. Okay, which we talked about before, because we did calculations with U, and it's in the Formula and Tables book, and they can, instead of kilograms, they can give you the mass of elements on the periodic table in terms of unified atomic mass, which is, I mean, it's arguable there's still an awful lot of decimal places, but it's a bit easier because there's no scientific notation. And then you just bring the scientific notation back in at the last minute, like when you're doing E equals MC squared. So we have done this before, this bit, because we've done particle. So this is where, like, normally this chapter is completely done before we do particle. So we're a little bit ahead of ourselves. So you do know what unified atomic mass is in terms of using it, but I suppose that's what it is. So they started out with atomic mass, which was basically defining everything as a multiple of the mass of hydrogen. And then in the 1960s, they changed it that everything was being defined as a 12th of the mass of carbon. Minor differences, but I suppose when we're dealing with such teeny changes in mass to produce our energy, those minor differences make a difference. They do actually make a difference. Because we are looking at like loads of scientific figures. Okay, so the mole. So a mole of a substance is the amount of that substance that contains as many particles as there are atoms in exactly 12 grams. This number is I'm going to start it again. A mole of a substance is the amount of that substance that contains as many particles as there are atoms in exactly 12 grams of carbon-12. I didn't say the last part. This number is 6.02 by 10 to the 23, and it's called Avogadro's number. So when I was saying if they ask this question, they're going to have to heavily scaffold it. The mole, the definition of the mole is on the Leaving Cert Physics course, but Avogadro's number is not. So if they want to ask you this question, they're going to have to kind of explain to you what Avogadro's number is. I mean, they're going to have to give you the number, but that's in the Formula and Tables book anyway. Okay, so I'm going to try and simplify it because I know that definition is kind of a bit mind-bending. But essentially, a mole of any one substance is equal to its mass number. So let me show you. Okay. I know I have this done already, but we can rub it out if we go. So how many atoms are there in 10 kilograms of lead-207? And then they give you over here the structure of lead-207. So they're telling us that the atomic number is 82. So this is atomic. And then up here, the mass number is 207. Okay. Now, from the concept of the mole, we say that 1 mole of lead contains Avogadro's number, which is 6.02 by 10 to the 23 atoms. Yeah? And then the only thing you need to get across is that 1 mole, don't know why I pluralized it, sorry, is the same as the mass number. Yeah. So 1 mole, and it doesn't have to be lead, as in it's just lead because lead is this. So 1 mole of any element contains Avogadro's number of atoms. In this case, 1 mole, you get it from here, is your mass number. So 207 grams contains 6.02 by 10 to the 23 atoms. And what I've done over here is just that mathematical process of going back to 1. So to get from 207 to 1, you divide by 207. And if you divide by 207 on the left, you divide by 207 on the right. So I took Avogadro's number, which is this number here, which again is a constant, and divided it by 207, which gave me 2.908 by 10 to the 21. And then this question was, how many atoms are there in 10 kilograms? So to go from 1 to 10,000 grams, I multiplied by 10,000. And again, if you do it on the left, you do it on the right. So 10,000 grams of lead contains 2.908 by 10 to the 25 atoms of lead. And that's how you do the Avogadro's number questions. Okay, so sorry, I'm trying to see how could they write this question that it would be workable without telling you about Avogadro's number. Do you know? So a sample of polonium-218, which is an alpha emitter, has a mass of 2.4 micrograms. Calculate the number of alpha particles emitted per second from the sample if its half-life is 3.1 minutes. So they've obviously given us Avogadro's number at the top, which is a big hint to use Avogadro's number. But if that question was asked on the paper, they would have to scaffold it. They'd have to ask you to calculate each bit as you go through the question, because they can't ask it like that, because you're not expected to know Avogadro's number. So anyway, right, so I think I'd like you to do that question 3. I'll put that into the journal for you. And then back up here, I just want to try find the number per second for sample containing. I don't know, let's go with 15 and 16. Sorry, I'm going to change 14 and 16. Okay, so have a look, higher level, have a look at 14, 16, and then have a go at question 3 down here. And yeah, ordinary level have their question to do. All right. Okay, I'll take any questions on that on Wednesday, and we can get hopefully the other chapter done, and I will see you in the morning for a practical.